Hi everyone, it's such a privilege to be here and to talk to you about Riverlane. We are a quantum computing software startup based in Cambridge, UK, but now also have a US presence in Boston with about 90 employees now. And what I want to talk to you about today is how control systems and work on control systems will make quantum computing useful sooner. So, why quantum computing? Why are we so excited about quantum computing? Well, I am a chemist by training. In a previous life, I was a chemist. And I am excited about quantum computing solving really thorny chemistry problems that will help us build a more sustainable economy. For example, if we want to go to a hydrogen-powered economy, we need to improve a process called steam methane reforming that produces the hydrogen. This is a catalytic process that uses a lot of energy, and we need to improve these catalytic reactions to reduce the amount of energy that goes into it. And we could revolutionize this, the R&D that goes into this, by being able to compute the properties of the catalyst rather than doing trial and error in the lab. On a classical computer, this is currently impossible. On a quantum computer, we would need 10 billion operations. We would need a machine that is able to do 10 billion operations on 5 million qubits. Now, I think you all know that today we have quantum computers that are amazing, that are heroic feats of engineering and physics. But unfortunately, they're around 500 operations on 20 qubits large. So we've got a really long way to go. Luckily, there's so many people here that are up for this challenge in terms of scalability and also in terms of the error correction that is needed to actually get to that sort of computer. So let me tell you a bit how today's sort of experimental setups look and how the different parts that we've been talking about come together to make a qubit or a couple of qubits. So this is an experimental setup that we have today. It's a bit complicated, so let me disentangle it for you. We obviously have lasers. This is an ion trap setup that send pulses to our atoms in a trap or to our ions. And these get modulated by acousto-optical modulators. And it is a very complicated control system that sends RF pulses or that produce the RF pulses to really modulate these laser pulses in just the right way so we get a qubit out of our atom or ion. So we at Riverlane are working on the control system, on making it more scalable, on making it ready for this big challenge of quantum error correction that we all need to face. So our control system is called Delta Flow Control. It is a scalable and error correction ready system. So it is designed with all the requirements from quantum error correction in mind and has a scalable, decentralized architecture. It has just the right kind of timing and pulse control and precision that people in the lab need to be able to concentrate on the physics. And it is intuitive and user-friendly with an amazing front end and software stack on top. It is also deterministic, so you program and you get what you program. And we are very proud to be working with the leading labs in the world, including academic labs like Tracy Northrop Lab in Innsbruck, but also commercial customers. We're currently focused mostly on atomic qubits, so cold atoms and ions, but we also work with superconducting and silicon qubits. So, what now? We are convinced that a better control system isn't only important for quantum computing, but that it will galvanize other discoveries related to AMO physics, for example, in atomic clocks, for example, in quantum sensors. So we are looking for partnerships with like-minded companies and institutions that want to make this process of building large-scale quantum computers and deployed quantum 2.0 tech like clocks, sensors, etc., to professionalize this, to make everything smooth for the user and make error correction and scalable systems. And this is why I'm here today. thank you very much for listening, and do get in touch.